Hi guys.
Hi, Dr. Das.
Hi. So let me
Hi, Dr. Das.
hi. Let me share the slide. Today's lecture will be on linear systems. It's again going to be a review, but you'll learn something new as well. Um, so how do I share? Okay, are you able to see my screen, the slides?
Yes.
Yes.
Okay, so we'll do a review of linear equations. Existence and uniqueness of solutions. Then we'll look at rank of a matrix, condition number of a matrix that some of you might not be so familiar with, and how to establish error bounds using the condition number of a matrix. Okay, so unique solution. Let's look at a very simple example. 2x plus 3y equals 4 and 5x plus y equals -3. And we want to solve it. We can rewrite this pair of expressions in terms of vectors and matrices in this form. So this matrix 2, 3, 5, 1 times this vector xy equals this vector 4, -3. And the solution can be obtained easily. Xy equals the inverse of this, 2, 3, 5, 1 inverse times 4, -3. And this will give you the solution. So we get x equals -1, y equals 2. And this can be viewed graphically. This is a unique solution. This is the graphical interpretation. So 2x plus 3y equals 4 is this straight line here. And 5x plus y equals -3 is this line here. And the two lines intersect here. And that's the solution, -1, 2. X equals -1, y equals 2. That's our solution. The solution is unique. Now let's look at this pair of linear equations. 2x plus 3y equals 4. 4x plus 6y equals -3. Now, if you look at the left side, here you have, at the top, you have 2x plus 3y. And in the next row, you have 4x plus 6y. So it's twice of this row, right? The left-hand side of the bottom expression is twice the left-hand side of the top expression, which means that if you multiply this by 2, you would get 4x plus 6y equals 8, right? But the expression wants 4x plus 6y to be -3, not 8. That's impossible, right? So what happens if we try to solve it using our previous method? So we have 2, 3, 4, 6, xy equals 4, -3. And then all we have to do is take the inversion, invert this matrix and pre-multiply it with 4, -3, and we should get our solution, right? But the problem is this matrix 2, 3, 4, 6 is a singular matrix. It cannot be inverted. Its inverse does not exist. Therefore, we cannot compute the solution. Graphically, let's see what's going on. This is the first equation, 2x plus 3y equals 4. This is the second equation, 4x plus 6y equals -3. There is no intersection because these two lines are parallel. And that's the reason there is no solution. Now let's take up this case. 2x plus 3y equals 4. Our first equation is the same as before. And the second equation is 4x plus 6y equals 8. What are the values of x and y? So we express these two expressions in vector matrix form, and then we already know that this matrix 2, 3, 4, 6 does not have an inverse. Therefore, we cannot compute the solution. And in fact, there are infinite solutions for to satisfy these two equations. Geometrically, this is what's happening. Both these equations are actually the same straight line. The second equation here is nothing but twice the first expression, correct? So the two lines overlap. Therefore, any point along that line is a solution. Therefore, there are infinite number of solutions. Correct? X equals 2, y equals 0 will be one solution, right? 2, 0. Another solution is x equals 2, y equals 0 is one solution. The other solution is x equals 0, y equals 1.33. X equals 0, y equals 1.33. 3 times 1.33 is 4. Right? And likewise, it will satisfy this equation too. 6 times 1.33 is 8. So we can see that when this matrix was invertible, then we had a unique solution. Otherwise, we have either no solution or infinite solutions. Let's delve into this a little further. So in general, this is what we have. We have n equations in n variables, x1 through xn. So we have a system of n linear equations in n variables. Now, in matrix form, we let the vector b be equal to b1, b2, all the way until bn, and vector variable x be x1, x2 until xn, and then this square matrix A be the matrix whose entries are these coefficients, A11, A12 until A1n, all the way to AN1. At the last row, you have AN1 through ANN. Now, with this notation, we can rewrite this set of linear equations simply as AX equals B. Right? And there's another way to write it. We can also write A as a block row vector of column vectors. A1 is a column vector containing this column A11 until AN1 of this matrix A. Then we have A2, not shown here, all the way to AN is this column, the last column. So I'm expressing this matrix A using its columns, A1, A2 until AN. Note that each column is also an n-dimensional vector. With this, we can also rewrite the above equation as this. This is AX equals B, right? This A1 until AN, this is A, and this is X equals B. This can be read off as A1 X1 plus A2 X2, not shown here, plus dot 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 until AN XN equals B. Note that each A here is an n-dimensional vector, and so is B. They're all n-dimensional vectors. Okay, now this is where we had a unique solution, right? In this case. Here, using the vector matrix notation, we express this matrix in terms of its columns. we have two columns, A1, which is 2, 5, and A2, which is 3, 1. And B is 4, negative 3. Okay. Now the column vectors A1, A2 are independent. They are in different directions. They're both two-dimensional, and they are in different directions. One is 2, 5, the other is 3, 1. Okay, another way of saying that is the span of A1, A2 is a two-dimensional space. In other words, the rank of this matrix A, this matrix 2, 3, 5, 1 is 2. Okay, the two are equivalent statements. Any two-dimensional point can be expressed uniquely as a linear combination of A1 and A2 because A1 and A2 are independent vectors. Any vector, any two-dimensional vector, they span 2 dimensions. So any two-dimensional point can be uniquely expressed as a linear combination of A1 and A2. Okay. In particular, B is a two-dimensional vector that can be uniquely expressed as a linear combination of A1 and A2 also. Right? In fact, this is what we want. This is A1 and this is A2 and this is B. And so some coefficient x1 times A1 plus some coefficient x2 times A2 should be equal to B, right? So this is a linear combination of the two vectors A1 and A2, right? And therefore, this is what we actually want. Where here we are trying to solve for x1, x2. In fact, what we're looking for is these set of weights on A1 and A2 such that their weighted combination, weighted linear combination with these weights x1 and x2 will give us 4, negative 3. Right? Okay. Now, what about the other case? Are there two cases actually? In both the other cases, no solution and infinite solution cases, we use the same matrix A, 2, 3, 4, 6. Here, A1 is 2, 4, and A2 is 3, 6. Are they independent of one another, A1 and A2? Anyone?
No, they are dependent.
A2 equals 1.5 times A1, right?
Yes.
So in fact, they point in the same direction.
Yep.
So we cannot express any vector B, any arbitrary vector B, uniquely in terms of A1 and A2, right? Now, the span of A1, A2 is one dimension. And the rank of A is also one. Equivalent statements. So any vector B cannot be expressed in terms of A1, A2. Okay. But if the vector B belongs to the span of A, then it can. So 4, negative 3, if this is our vector B, this does not lie in the span of A1, A2. B does not lie in the span of A. This is shorthand for span of A1, A2. Span of the columns of this matrix A. And therefore, we cannot find any X and Y to, oops, this is X1 and X2, rather, that satisfies this expression with B equals 4, negative 3. However, in the other case, when B is 4, 8, now 4, 8 does lie in the span of A1 and A2. In fact, 4, 8 is if you just take twice of A1, you get 4, 8, right? If you add A1 plus 2/3 of A2, this is not A1 plus A2, this is A1 plus 2/3 of A2. Okay, 2/3 of A2, you again get the same 4, 8. Right? Or multiply A2 with 1.333. 1.333 A2 equals 4, 8. So there are so many ways you can express this 4, 8, this vector B in terms of A1 and A2. That's because B belongs to the span of A. Okay, thus we have infinite number of solutions. We have infinite number of ways in which B can be expressed in terms of A1 and A2. Okay. So we have 3 cases. And now let's look at that matrix A using its determinant. If the determinant of A is non-zero, then the matrix A is invertible. There's a unique solution. And if the determinant of A is 0, then the matrix is singular, non-invertible. In this case, it was invertible. Non-singular and invertible mean the same thing. Singular and non-invertible mean the same thing. So this matrix here is singular. You cannot have its inverse. If B does not belong to the span of the columns of A, then no solution. If B belongs to the span of the columns of A, then we have infinite solutions. And this is our notation. Span of A is shorthand for span of these columns, A1, A2, until AN. Rank of A is the dimensionality of the span of A. In our previous example, when the span of A was 2-dimensional, then the rank of A was 2. And in the other case, when the span was 1D, the rank of A was 1. Here's another example. Now, this is a slightly bigger matrix. We have 3 column vectors, 3 dimensions now. A, which is 3, -1, 2, B, which is 2, 2, 0, and C, which is 8, 0, 4. And we make up this matrix whose columns are A, B, and C. Rank of this matrix is 2. Its columns are A, B, and C. So it's not a full rank matrix, right? Its rank is only 2. What does it mean? It means that A, B, and C are not linearly independent. They span a 2-dimensional space. And we can see why they're not linearly independent, because C is equal to twice A plus B. And span A, B, C is 2D. Okay? Here's another example. A is 0, 0, 2, B is 2, 1, 0, C is -1, 0, 0. We take A, B, and C and form this square matrix whose columns are A, B, and C. And the rank of this is 3. What does it mean? It means that A, B, and C, these 3 column vectors, are linearly independent. You cannot express any one of this as a linear combination of the other 2. In other words, the span of A, B, and C is 3-dimensional. Last example. This is A, 2, -1, 0. B is now -1, 2, 1, 0. C is 6, -3, 0. Form the matrix out of A, B, and C, and we see that the rank of this matrix is nearly 1. Why so?
Because all vectors are dependent.
Yeah, 2 of them can be expressed in terms of as a multiple of any one of them. In fact, you can see right here I've written it. B is equal to negative A, so we can express B in terms of A alone. C is also a multiple of A. C is, in fact, 3 times A. Or we can say C equals twice A minus B, etc. Right? So there's only one independent vector here, and the other 2 vectors are dependent on it. They're just they're in the same direction as the first one, except to a different scale. So all we have to do is multiply them. And the span of A, B, and C is 1-dimensional. Okay? Any questions?
No.
Okay. Rank. Rank is the number of linearly independent columns AJ of A. Rank of A is the same as the rank of A transpose. These are properties of rank. Rank of an M by N matrix is less than equal to the minimum of M and N. Okay. So if you have a 5 by 3 matrix, what would its rank be? 3 or less. The minimum of the 2 dimensions. Okay. It cannot be 5, even if it's a 5 by 3 matrix. Rank of the product AB is less than equal to the minimum of the rank of A and the rank of B. Here's I'll give an example and how to geometrically interpret this. So A is an 8 by 5 matrix. What's the maximum possible rank of A? 5, right? Yeah. B is a 5 by 9 matrix. Okay. Rank of A, B, it can only have rank 1, 2, 3, 4, 5. By definition, by the way, only the 0 matrix has a rank of 0. Okay, rank of the product AB, as per this inequality, is always less than equal to 5. Geometrically, let's try to interpret this. So let's begin with the 9-dimensional space. Okay. We have B is a 5 by 9 matrix. We take a 9-dimensional vector X and let Y equals BX. So Y will be 5-dimensional because B is 5 by 9, correct? Right? Y equals Bx. This is 9 by 1 vector X, and this is 5 by 9.
Yes.
So Y will give you a 5-dimensional vector, right? So Y is in a 5-dimensional space. So from 9 dimensions, we project these two 9-dimensional points to 5-dimensional. And then what we do is Z equals AY. Okay. Here Z is, we take this Y, which is 5-dimensional, and find the product AY. A is 8 by 5. 8 by 5 matrix, and then 5 by 1 vector will give you an 8 by 1 vector. So Z is a 8-dimensional vector, right? So we take something that's 9-dimensional, compress it to 5 dimensions. We are getting rid of some kind of information, right? I'm using information in a very informal sense. And then we are trying to increase the dimensions from 5 to 8. And we cannot do that, right? So what happens is, we'll take randomly generate all these points Y, okay? And then compute, all these X's randomly, and then find Y, and then find Z. Okay, what will happen is all these points Z will lie in a 5-dimensional hyperplane within this 8 dimensions. Okay, was I clear about this inequality?
Yes.
Yes.
Okay, now here's graphical interpretation. Okay, now this is X. X is any point on this three-dimensional sphere. Okay, it lies on the circumference of this, on the surface of this three-dimensional sphere. Okay, it could be this blue arrow here, this red arrow, it could be this green arrow, it can be anything else, as long as it's from the center to the circumference. Okay, so X, and now A is a rank 3 matrix. Okay, so AX will give you some other point, and all these points will form this three-dimensional hyperellipse, ellipsoid. It's this egg-shaped region. Okay. That's because A is three-dimensional. Excuse me, of rank 3. Now, what if A were of rank 2? This is what would happen. We do the same operation. We take all infinite points on the surface of this three-dimensional sphere. All these points will project to something, to this two-dimensional ellipse, which is two-dimensional. It's not three-dimensional. So we are getting, we are seeing a loss of one dimension. Okay, because the rank of A is 2. If the rank of A is 1, then all these points would land up in this straight line segment. Okay, because A has rank 1. Any questions with this illustration? Okay, so the next topic is condition number of a matrix. Now, informally, the condition number of a matrix tells you how good the matrix is. A square matrix, A is a square matrix. Okay, and the condition number, we will follow both notations. Kappa of A will denote the condition number, or COND will write condition number of A in this form, depending on our convenience. And the condition number of A is defined as the norm of A inverse times the norm of A. And by definition, if A is not invertible, then the condition, of course, then A inverse does not exist, right? In that case, by definition, the condition number is infinity. The higher the condition number, the worse the quality of the matrix, okay, informally. So it's good to have a small condition number. The condition number always lies between 1 and infinity. The condition number of the identity matrix is 1. That's best. Okay, the best possible situation is when you have a matrix with condition number 1. Now, when the matrix is singular, that is, it's not invertible, it's determinant to 0, then the condition number, I just told you, by definition, the condition number is infinity. Now, we want to improve the condition number by reducing it, right? The bad news is multiplying the matrix A with some scalar alpha will not change the condition number. So the condition number of A will be the same as the condition number of alpha A, where alpha is some scalar. The condition number of A is the same as the condition number of A inverse because of this definition. What's A inverse inverse? A, right? The condition number of a diagonal matrix, you find which one is the highest of them, absolute or numerically, which is the highest of the diagonal elements, and which is the lowest, which has the smallest numerical value, ignore the signs, and then that ratio, maximum over minimum, that's the condition number of the matrix, of the diagonal matrix, which actually tells you why the condition number of the identity matrix is 1, because D1, 1, D2, 2, all the way until Dnn, all these diagonal elements will be the same, 1, right? And therefore the ratio shall be 1. So these are properties of the condition number. How is it useful? Here's an example, okay, before we go to its use. So this is a matrix, 1, 1, 1 plus epsilon 1. When epsilon is 0.1, the condition number is 42. Not that bad, right? The condition number is between 1 and infinity. At least it's not 500, 5,000. It can go up to anything. So this is acceptable, maybe, depending on what we want to do with this matrix. Epsilon is 10 to the negative 1.1. So this matrix is close to singular. If epsilon was 0, this matrix would be singular, right? 1, 1, 1, 1. Now, epsilon being 10 to the negative 1 gives us a condition number of 42. What if epsilon is much smaller? What if epsilon is 10 to the negative 3? Then this matrix would look even closer to 1, 1, 1, 1, right? The condition number is now 4002. By the way, it's just a coincidence that it's 42 here, the digits 4, 2, and here you have 4 and 2. That's just a coincidence. It can be anything else. Okay, so it's 4002. The condition number went up so much because epsilon got reduced. So it became closer to a singular matrix, 1, 1, 1, 1. Okay, when the condition number is larger, then A looks more and more singular. Sometimes condition numbers can be like matrix. From the look, you might think that this is a good matrix, but when you look at the condition number of this matrix, it's 15514. It looks misleading here. It doesn't look to be very close to singular, but like I said, appearances can be deceptive. The condition number of H is actually very high. It's a very poorly conditioned matrix. Now, let's see one way we can use condition numbers. We are to solve AX equals B. Now, the first step is we need to make sure that this is indeed solvable. Okay. That is the problem of finding X in AX equals B is well posed. That's the technical term for it. And our goal is to numerically find X. Okay. Now, A is, suppose we know A, but B, we don't have the actual value of B. We only have an approximate value of B, which is B hat, which is B plus the error delta B. Okay, so this is a perturbation in B, B plus delta B. And it could be due to experimental error when B was obtained experimentally. And so delta B will contain experimental errors, noise, that is. Otherwise, B due to round off or truncation errors in the computing itself, that introduces errors too. So in that case, we don't have the exact value of b. We have b hat, which is b plus delta b. Okay, but our goal is to find x. Because we don't have the real value of b, we only have b hat, we have to solve this expression, ax equals b hat, right? So we won't get the real value of x, we'll get an approximate value of x. So we will get, when we solve ax equals b hat, we will get x hat, which is equal to the real value of x plus some error. Now, likewise, I'm not going to go through this, but there could be an error in A also, in which case A hat is equal to A plus delta A. Delta A would be the error in A, and again, solving for x would give us x hat equals x plus delta x. But we'll focus on the first one, and my slides do have this, and you can look it up. The derivation is very straightforward. Okay, so in both cases, the numerical estimate x hat has error delta x. Okay, now let's look how much is the damage. If delta b is our error, can we estimate to what extent will x hat be different from x? In other words, what will be the approximate range of this delta x? Okay. So here's one important lemma. So this is the norm of delta x divided by the norm of x. What is x? The real value, right? X plus delta x is what we will get, which is x hat. And so this is, you can think of this as the fraction error in x, right? Delta x, norm of delta x divided by norm of x. And this is upper bounded by this. So look at this ratio here. This is norm of delta b. Delta b is the error in our estimate of p, and this is the real value of p. So this is, again, think of this ratio, norm of delta b over norm of p, as some kind of fraction error in b. So fraction error in A is less than equal to condition number of, fraction error in X is less than equal to condition number of A times the fraction error in B. Okay. If the condition number is, let's say, what did we have here? 15514. Okay, and suppose we have 10 to the minus 5 as the fraction error in B. So our measurements are very accurate, just 10 to the minus 5. So 0.001% is the error. What will happen? The condition number is that high, 15514 or something. We'll get a large fraction error here, right?
Get a higher bound.
Yeah, the bound will be very high. Now let's prove this. Now, if we have all the true values of A, or if we have the true value of B, then AX equals B. We would get X, the real value of X, the correct value of X, and it would satisfy AX equals B. But unfortunately, what we have is B hat. Correct? And so when we not B is not available, what we have is B hat. And when we try to solve it, AX equals B, the value of X we get is X hat, which contains errors, right? So AX hat equals B. Now, remember these two, ax equals b, ax hat equals b hat. So I take this ax hat equals b hat first. And since x hat is equal to x plus delta x, we have ax plus delta x equals b plus delta t. Now I open up this parenthesis. Ax plus a delta x equals b plus delta b. But you see this? Ax equals b. You have ax here and you have b here, right? And so since ax equals b, we are left with a delta x equals delta b. Implies delta x equals a inverse delta b. Okay. Now let's apply the Cauchy-Schwarz inequality on this side. If you take the norm of the product of two matrices or matrix vectors, whatever, vector is a kind of matrix, right? The norm of the product will be less than equal to the product of their individual norms. So the norm of this delta x, which is equal to the norm of A inverse delta B, will be less than equal to the norm of the product of their norms, which is norm of A inverse times the norm of delta B. Okay? So this is our first expression that we need. What's our goal? This, to establish this upper bound relationship. Okay. So we have this expression now. Now let's take the other expression, ax equals b. Now, when we apply the Cauchy-Schwarz inequality, what do we get? Norm of A times the norm of B will be greater than equal to norm of A times the norm of X will be greater than equal to the norm of B, correct? So this is our second expression. What I'll next do is, I'll take this expression in the left-hand side and right-hand side separately. I'll take the numerator from this expression here and the denominator from this expression. Since I'm taking this and this as the denominator, 1 over this will be less than equal to 1 over norm of b, right? So we have less than equal to sign here. So what I'll do is on the left hand side, delta x divided by, I skipped a step, sorry. So x is greater than equal to b over a. And now I'll do the same thing. Divide this with this. Numerator here and denominator here. Okay. So left side will be delta x over x less than, because this appears in the denominator, less than equal to norm of A inverse norm of delta B, which is norm of A inverse norm of delta B times, this is the denominator, so norm B divided by norm A, we have to take its reciprocal, so it's norm A divided by norm of B. Do you see how I got this expression for this from this and this?
No, Dr. Das, I think I'm a little lost.
Okay, let's say 3 is less than 5. Okay, 10 is greater than 7. Can't you infer that 3 by 7 is less than 5 by, what was it? No, I forgot the values. This is 3, this is 5, this is 10, this is 7. Okay. 3 by 10 is less than equal to 5 by 7, right? Or, I'll make it clear. I try not to use the whiteboard because if because first I'm left-handed, I'm using a right-hand cursor and a mouse, and secondly because it's not the kind. So we have A is less than equal to B, and we have C is greater than equal to D. So from these two, I'm saying that A over C is less than equal to B over D.
Okay, Dr. Luis, I think
Okay.
I understand. Yeah, thank you.
So back to what we had was this. Where were we? Okay. So now you get, so you got this now, right? From this expression and this expression. Now, what is this? Norm of A inverse times the norm of A.
Condition number.
It's the condition number, right? This is the fraction error. I'm using the word fraction in a loose sense, okay? Since we're using norms of vectors. Norm of delta x divided by norm of x. The fraction error in x. This is the fraction error in B. And bingo. That's what we wanted to prove. Now, it's very common when you look at other derivations, not in my course, but when you read the journal papers, IEEE transactions, it's a very common trick to use the Cauchy-Schwarz inequality to establish bounds. It's very common. Okay, so that's something that you need to know. And this, the reason I showed you the proof is so that you get familiar with Cauchy-Schwarz inequality, using this inequality to establish bounds. And what I would request you guys to do is look at the error in A. It's very simple again. So the lemma now is the fraction error in X is upper bounded by condition number of A times the fraction error in A, norm of delta A over norm of A. And we again begin with the true expression is this. This is now the, might as well, how much time do we have? I think we have time. So we have time. I might as well go through this proof. So this is what we have. Since we don't have the real value of A, we have A hat instead. When we try to solve it, we will land up with X hat as the solution, right? Which has an error, delta X. So A hat X hat equals B. We assume now that B is error-free. The only error is in A. So A hat X hat is B. Now, A hat is equal to A plus delta A. And X hat is equal to X plus delta X. So what we have is A plus delta A, X plus delta X equals B. What do I do next? Open up the parenthesis, right? And I'll make a small approximation here. What will that be? If delta A and delta X are small, which term can we neglect, drop? Their product, right? So if we neglect delta A, delta X, Now this is just an approximation. Okay? So then we'll end up with AX plus delta AX plus A delta X equals B. Right? Now, what do we do next? We know that AX equals B, right? Whence delta AX plus A delta X equals 0. Or A delta X equals negative delta AX. Or delta X equals negative A inverse delta AX. Right? Okay, can anyone guess what's the next step? The Cauchy-Schwarz inequality. So delta X is less than equal to the norm of the product of these three will be less than equal to the product of their individual norms, right? So this will be less than equal to this. And you can, since we're taking norms, you can drop the negative sign. Norm of A inverse times the norm of delta A times the norm of X. Okay, so this is what I have. And then what I do is I multiply and divide by norm of A. Then delta X, I take to this, I put this as the denominator on the other side. This, not delta X, excuse me, norm of X. Norm of X, I bring to this side. So what do I have? Delta X over X equals or less than equal to norm of A inverse times this ratio, norm of delta A over norm of A. What is this? This is the condition number. And this we have a norm of delta A over norm of A. This is the ratio or the fraction error in A. And this is the fraction error in X. Okay. Do you want a little demo? Of norm in MATLAB? Do you want that? Or are you good? And then the rest is just a rehash of what we did. I think let's do a little demo in MATLAB. So I'll share the screen. Are we able to look at, oh, I'm somewhere else. Okay. Okay, I just created an arbitrary direct folder called temporary. Okay, let's say epsilon equals 0.1. Okay, and then A equals 1, 1, 1 plus E 1. Correct? What's the condition number of A?
42.
42. Okay, now let B be equal to whatever. B be equal to, let's say, 2, 3. Okay. No, not that way. Let's say x equals to 3. Okay, I'm trying to fix x first. And then b equals a star x. Okay, so this is my b here. So this is my matrix A, and this is my vector B. Okay, and I want to find x, right? But we already know that the value of x is what? 2, 3. What I'll do is let me add a little perturbation to B. B1 equals B plus 0.01 star random 2 by 1 random vector minus 0.5, so that it's discrete. .01 times this. So this is my B with my error. Okay. It's different from B. I introduced 0. So this, look at how RAND works. Basically, this is a random number whose random vector whose coefficients are between plus 0.5 and minus 0.5. And then I multiplied it by 0.01. Okay. Now, x1 equals inverse of A star B1. This is x1. And how does it compare with x? Dx, delta x, the error, is equal to x minus x1. Okay. So this is, what's the fraction error? Norm dx divided by norm of x is the fraction error. 0.0079. Okay. What was the fraction error in B? dB equals B minus B1. And the fraction error in B was norm dB divided by norm B. Okay, this was, so 6 e to the negative 4. And because our condition number was, what was the condition number of A?
42.
42. So star 42.0267. That's an upper bound. It's a loose upper bound. Okay. Now let's redefine A. E was equal to, now let's make E this much. Or should we go one more? We'll give a huge error. Let's see. And A, we define A equals. Okay, now A is much closer to being a singular matrix, right? Okay, so now what do? We know the value of x. Okay, we know, okay, we have B1 is the approximate value of B, right? We don't have the real value of B, we have the value of B that we have is B1. So our x1, this is the new x1, okay, will be equal to inverse of A times B1.
Yeah.
Oh no. See how big it is. Right? It's too big. Actually, let's maybe I should have used 0.005 would be a safer bet. Okay, A equals this now. So it's still quite close to singular matrix. Condition number of A is now, it's much higher now. Okay, now let's try to solve it. X1 is this. So you still get so much. But you see the reason, right?
Yeah.
So let's do, what is delta X then? Error is so much. And what's fraction error? Norm, this is a fraction error. 15, the error is 15 times the actual norm of X, right? And what the fraction error in B? This. But because the condition number, so ans star condition number of A is this much. Why did I get 15? Norm of X, right? I might have done some. Did you observe any mistake that I did?
I think that's correct.
Okay.
You didn't recalculate dB, I don't think.
Oh, maybe DB. Right.
That's right. Anyway, you got the idea. Did I have to calculate dB? But whatever, you see what's going on here. Okay.
I think the error in B, like we had to recalculate B.
Oh yes. Oh yeah, I got it.
Yeah.
Yeah.
Yep.
B and then B. Same perturbation, right?
Yes.
Yeah. So now dB equals B minus. Yeah. Norm. This much. And now we have to X1 equals. Oh, okay. Yeah, I see. I should have recalculated. This is X1, and now dx is equal to this. No, it's not that bad. Norm. This is the fraction error in X. And the fraction error in B is much less. But what's the condition number of A now? 800. So this condition number of A times this is, and what's the condition, this is the fraction error in X now, 0.32, and the upper bound is 0.52. So that shows you why this is valid, right?
Yeah.
Okay, any questions?
I don't have any right now.
Okay, so just a quick recap of what we did. So we looked at linear equations, ax equals b, same number of rows and columns. So we have n expressions in n variables. And so if the matrix A is invertible, non-singular, then the unique solution is x equals A inverse B. Otherwise, you can land up with infinite or no solutions. Okay, now I introduced you a term, Ax equals B. This check is, does it actually have a unique solution or not? Finding out that problem is called, or finding the answer to that problem is called the same thing as, is the problem ill-posed or not? If the problem is ill-posed, then it doesn't have a unique solution. If the problem is well-posed, it has a unique solution. Now, it might have a unique solution. It might be well-posed. Then the next step is it ill-conditioned or well-conditioned? I don't have in the slides these two terms that I'm trying to introduce to you. Ill-posedness answers this question, is there a unique solution or not? And then after you're satisfied that, okay, there seems to be a unique solution, it's well posed, then you go ahead and see, is it, will an algorithm be able to find it or not? That's the next question that you should ask, right? And that question can be asked in another way. Is the problem well conditioned? Okay, and
I have a question.
You have to check the condition number.
I have a question.
Sure.
Is there a metric to check if it is ill-posed similar to the ill-conditioned?
Yeah. Well, there are, for really large matrices, there are a number of approximate techniques.
Okay.
We're not going to get into that, but this is the day of big data analytics, right? So in big data, it's a very frequently asked question. How do you estimate the determinant or the norm or the condition number of a given matrix? 100,000 by 100,000 matrix. Okay. So you do some estimation before you actually begin trying to solve the problem. Anyway, and then we saw what the rank of the matrix was, and it's equal to the dimensionality of the space spanned by its column vectors. We saw that the condition number was defined as norm of A inverse, norm of A. And what's norm of a matrix? By definition, it's it can be any LP norm, it can be the Frobenius norm, but normally it's the Euclidean norm. Unless specified otherwise, everywhere we'll assume that it's the Euclidean norm. And we saw the error bounds. The condition number is used to establish error bounds, and we saw a little demo of that too. Okay. And don't forget this. Maybe if I had a little more time, we could have seen this too. Let's see how much time we have. No, it's going to be 3:45. Can you guys hang on for like 10-15 minutes? Anyone? If you don't have to go right now, then I might demo the other thing that this, what happens here, the ellipse that's forming.
Yeah, I have 5 minutes. I can stay 5 minutes.
Okay, good.
Yes, please.
Yeah, it's fine.
I accidentally, I'm so sorry. Oh, remove this one. Okay, so oh, there's something, a function called demo. Okay, I'm just creating an M file demo1, and let's have a equals, let's define a rank 3 matrix. In our example, where if you look at the slides, we had the rank 3 matrix was O2 -1, O1 0, 2 0 0. If you look at slide number 12, can you remember that? And tell me when I go back to the other screen. O2 -1, O1 0, 2 0 0. O2 -1. What was the next row? O1 O. And what was the last one? This, right? Correct? Okay. For X, no, will generate 100 points. I usually don't use I because I is inbuilt. It's -1 in MATLAB. So let's use K equals 1.
Hello. The third row will be 200.
Oh, 200.
Yeah.
And this is rank 3. Okay. So now X equals rand 3,1 minus 0.5. So now I'm generating a random X, and then X equals X over norm X. So now it's a random unit vector. Okay. Then Y equals A star X. Okay, then subplot 2, 1, 1, hold on, then plot X, comma, will this work? Oh, plot 3. I hope the command is plot 3. Then two, 1, 2, plot 3, Y, and let's color this R and this B, and help plot 3. plot x1, x2, x3. And we'll just do the same thing with y. And I'll add a hold off at the end. So plot 3, why did it plot and 2? Well, first of all, it should be 1, 2. I'm not so familiar with 3D plots. 2D plots at work. Okay, now plot 3. What did plot 3 give? This is what plot 3 should give. Running the program. It shouldn't take such a long time. Something's fishy. It shouldn't take such a long time. Oh, I don't know why it's not showing the third axis. Any reason why, but
I believe it is due to the subplot. Not sure if that is the reason.
Yeah, maybe what we can do is figure 1, if possible, and then figure 2. Maybe subplot the figure 2. Maybe you're right. Yeah, I think you're right. Oh. Well, you can see the points being plotted one after the other now. Did I do figure 1 and figure 2, or yeah, figure 1 and figure 2. Now, while it's going on, let's no, it doesn't even allow me to. So we have to let it blink 1,000 times. annoying.
Maybe, can it be that the definition of the matrix, because if there are linearly dependent columns, then it will project it in
Oh,
like
this is figure
2D. Yeah,
No, let's see what. But why is this being not being
yeah, at least that should be 3D.
right? So anyway, let's try it with what's the rank of A? Rank. Rank of A is 3. Now let's try a rank 2 matrix. Or shall we go for a rank 1 matrix right away?
Either way is good.
O2, let's try, let's go for a rank 2 matrix. O2 -1. How about this? This is 0, 0, 1. And this is, no, 1, 0, 1. And the third one, let's just add up the first and second rows. So 1, 2, 0.
2, 0.
Okay, so the rank is now 2. Now let me reduce the number of points to 100 and carry out this thing. This is, well, we can't see with this many points now. But anyway, to make this experiment a success, so now let's use a rank 1 matrix. So -1, 0, 0, -1. Let's make this 2, 0, 2. You can clearly see that the rank of this matrix is now 1. Now you can at least see that all the points are appearing in a straight line. Okay, so I don't know. Maybe I should have used mesh 3 or something. I don't know. But at least you see what's going on.
Yeah.
Okay. So we'll meet in the next lecture.